Thanks very much for colleagues. I have Lorne Clark from the University of Alberta, Canada with me. This is the American session of the bi-monthly Education Healthcare Facilities Subcommittee. We were talking a bit about the feasibility, the imperatives, the drive to use system grounding of campus power systems to reduce fault current. That's important when you're wiring up 100 or two substations at 13.2 kilovolts and you've got guys working on it. You can limit your fault current down to about, well, actually you can scale it according to any fault level you want, though you'll find variations in that because of the length of the feeders and the cable types, et cetera, et cetera. So Lorne Clark is a colleague of several years now, and I wanted him to talk a little bit about why it is, or his perspective on the particular problem of migrating to impedance resistance grounded power systems, campus power systems. So I hate to make you repeat it, Lauren, but I thought at least as a record of work, we can keep the discussion alive. Could you just summarize what you said? What is the perspective of the University of Alberta system, which is what? It's about a 50 megawatt system over there you've got? Or MVA?
Well, it runs at about 50 on average. I would say it's a 90 MVA capacity system. We've hit 76 MVA at our nominal voltage is 13,800 volt. We have not implemented neutral grounding. We have a solidly grounded system, and our perspective is that there's certainly cost involved with it, but there's also there's a labor component that sometimes is missed. When you have a neutral grounding resistor and you have a ground fault, it enables you to keep your system running. You don't have to trip, which is one of the big benefits of it, but you also have to use some devices to basically track down where that ground fault is. Depending on how much money you've thrown at finding where the ground faults are in terms of permanent infrastructure, you also can need some flexible CTs that have to go around cables and cable trays, my understanding, to try to track down exactly where that fault is. So sometimes it can be difficult to find, and there's going to be a labor cost component associated with that. And that's part of the reason we haven't implemented it at the University of Alberta. And when you have a solidly grounded system, your fault level is higher for sure on line to ground faults, but you know exactly where the ground fault has occurred because it's often results in some visible damage.
Okay.
So well, the good thing about having a neutral grounded system is that you don't have that damage on line to ground. It doesn't induce other types of faults like phase-to-phase faults. It won't help you with that. But the line to ground faults are certainly most common type of fault. So for personnel safety, I agree it's a better way to go. For the labor component, it's maybe actually more expensive than a solidly grounded system.
Mm-hmm. Well, a couple things. A couple comments. One is that I think you're probably primary selective like we are. Is that right? Yeah, you're main time main up the service. And what we did many years ago is we would install on each of the feeders. The feeders will run about roughly up to 2 miles, and we may have, let's say, up to 20 substations on it. On the outgoing feeder, as we took the primary switch that would go from one building to another, we would install a magnetic device that responded to the change in fault, and it's actually an indicator, and that allowed us to it was a marker. Again, we had to go in each of the substations. We could actually tell by what buildings were out. You can get a good guess at the powerhouse if you're going to have a cable failure. That you can start searching. It could be 10 buildings, it could be 20 buildings. So what it does is that device, and I suppose I could call it up here on the web so you can see what it is. But we installed them. We actually drilled holes in the cladding of the older substations on the outgoing feeder, and that gave us a little an indicator. Are you familiar with those, Lauren?
Somewhat.
Yeah, okay. Well, I'll show you what we did with them, and what I mention it because that's one of those candidates for if we want to talk about a smarter campus power system. We've already got a lot of instrumentation in our substations already. And maybe there's building automation controls. It is really it's about $5,000 a control point. If we were to say if we could charm the building automation guys into letting us say yes or no through the building campus automation system, then we would pretty much know that when that fault occurred between building A and building B, that fault sensor, which was magnetically tripped from the fault current itself, could be identified. So that way we kind of know instantly, more or less instantly, where that darn thing is. I think some of the utilities actually have more sophisticated. I think you mentioned a donut type of device that goes around feeders. It probably works on the same magnetic principle, but then again, it's trying to get how do you get that signal back? So when the policymakers and the regulator types want to talk about smart campus, I have a very specific example of how a campus power system can be made smart, which is since it's not a life safety signal, we don't have all the issues regarding use of the life safety network for sending a signal about a fault trip. So that's item one, using those. There's another, I think it's Schneider. I believe that there is a way for you to place instrumentation at the outgoing feeder, say up at your power at the service, that when you that you can actually scale its sensitivity and get a readout, and through the magic of firmware, you could actually identify how far down that feeder is. Maybe it's 2,000 feet down the feeder, maybe it's 10,000 feet down the feeder, but you can actually pick it up there. Now, are you willing? Does it happen enough? Well, now we get into the economic question, which is always what we have to talk about. And we feel that in campus environments, and obviously you're one, I wanted everybody to see your campus power system here. These power systems, a forced outage, one that you couldn't plan for, will run $100,000 to $1 million a minute. If you get into research and you're not able to swing over, you don't have an automatic main time A on your substations, you will you'll run up $1 million a minute type of a loss. So it's again playing the statistics, but I thought I'd put that out there as two remedies, two possible remedies that are out there. Maybe we can get one of the manufacturers to talk to us about that at some point, how you could more ease. In fact, we ought to put that on our wish list, as if we need anything more to add to it.
What voltage level did you implement high resistance grounding on for your network?
No, we didn't. University of California. I am out there with my little mini campaign to at least look into it. I think the priority would go to hospital systems, because they're the ones that hospital systems that are typically primary selective, and they may or may not have a district energy system, and they may or may not have a load shedding regime. But it strikes me that you can justify the cost, the remedial cost of installing more sophisticated fault sensing instrumentation, and obviously the migration to neutral grounding in a hospital system. Maybe not in a larger campus, although some of the research campuses are pretty gnarly. I'm not mistaken. I do have some colleagues at couple of federal labs. Maybe we can talk to them. My guess is that because it's a federal government, they're not as capitalized as well as they could be. So we are not, and that's why we'll have Jerry here next week or in 2 weeks talking about it. We also know that there's one up at the University of Washington.
Okay, I mean, I totally agree with you. I mean, industrial facilities have been using neutral grounding for decades to improve plant reliability, because they just, a downtime, like you say, costs huge dollars, and specifically in hospitals where you have, such huge life safety issues, it really should be implemented there. Like, we should be looking at what other sectors of industry, like the industrials, have done to improve reliability, and be looking at implementing those types of things if it makes sense. And I think that does make sense, especially in the context of hospital systems, which is probably part of the reason why you're seeing it now weaving its way into data centers.
Yep, yep. So here we have your campus. Where's your powerhouse here? Somewhere we've been through here before, have we not, Lorne?
Yeah. Just trying to.
I see Harvard.
On the south. Yeah, you see where the circle there is on the bottom lower part of your screen?
Yeah, excuse me.
Zoom into that area.
Just a second. I think somebody's struggling to get in. Hello, Mike speaking. Okay. Well, there's a trouble. People are still having trouble logging in. I don't understand why so many electrical engineers have trouble logging in. They're asking for personal help, and I'll have to give it to them next time. It sure seems to me it's easy to click on the link. Am I mistaken here? All you have to do is click on this link. I don't know what. I'm not gonna get too cranky about it, but you just have to just click. For my colleagues who will be listening to this video, just click this link right here. You click this link right here, and you're in the meeting. Okay. Getting back to your Matt, where do I need to go again, Lauren?
So on the south part and about the center of the screen, there's right there. Just zoom into that area.
That looks like a water treatment thing there. Isn't that what that is? What is that?
So that's our thermal energy storage tank.
Oh.
But not to be confused with it's not for power storage per se. It stores chilled water. We charge the chilled water tank in the evening or in the nighttime when power is cheap, and we discharge it during the day when power is expensive as a financial hedge.
I like that. I have a presentation in my mind's eye at some point here in the future, so that's interesting. Let's see what that thing looks like. I think we have been through that. Can we see what it looks like in front? It looks like it's got a fancy front there. Let's see. Well, this is nice. I can see the president and the regents walking this down. I mean, it's not.
There's the tank.
Yeah, very interesting. Interesting.
If you keep turning around, you'll see the heating plant.
Oh, yeah.
Across the...
Right here?
I think you went too far. Yeah, see, on the left-hand side of that? So what you're seeing, you want to stop for a second. See the big brick building on the right-hand side?
Right here?
That's the heating plant.
Oh, right here. So I'll put that on this. Okay, very good. All right. Well, so on our agenda is getting you to talk a little bit about your power system. We've got Michigan State, we have Michigan Tech, we have University of California, we have Texas, and I'm looking forward at a time you can remember that my philosophy is you don't need to do a big PowerPoint on it. Oh, MIT did one too also. The people that know most about the power system are very often not PowerPoint meeting going types. They don't have the support, or they don't have the time, they're putting out fires like everybody else. So we can simply talk about your power system just like this on Google. Maybe if we're lucky, if you have a one line. So just put that out there. So just to finish up this particular issue, the resistance grounding thing, I mentioned that just because we do have one of the IEEE recommended practices that is up for public review, and it's basically, this is the new version of what we used to call the Green Book, and
okay, yep.
And so I believe that will this take you to the place where you are. So this is the project, and let's see the comments. Oops, I didn't put the link on this one. So I will obviously mention comments. If I'm lucky, I'll have somebody smart like David Shipp or Tammy Gammon or Sergio Panetta, and they will try to drive some of these ideas. I mention it because standard of care is an ongoing discussion. It's an evolution. Everyone understands the standard of care in utility systems. They understand it in building systems. But we are in that, as you say, in that in-between area where there isn't none and where you need to write it. We kind of know instinctively by the pattern of our success, or at least the lack of failure of what we're doing, but we still need to write the standard of care. So my intention is to get that in there. That's the nature of my comments. So anyway, so I think that's kind of it for that particular issue. I don't want these calls to last too long. We can continue talking, but I did want to vet this issue of resistance grounding and why I keep hammering away at it.